All right, let's continue our course, my lectures. Sorry, let's continue our course. And my name is Professor Lajimi, Lajimi. I got my PhD from University of Waterloo and my master's from École Polytechnique Fédérale de Lausanne. Let's continue our discussion about directions in multivariable systems. For a scalar system, as you know, y is equal to GD, the frequency domain gain is the absolute value of y omega, where d omega, and then gj omega, d omega, or d omega, we simply replaced the output with transfer function at j omega, pre-multiplying the input. So we had this one, and then we replaced that with this multiplication. And then, as a result of simplifying this fraction, we've got only the magnitude of j omega. In SISO systems, gj omega is a single complex number, so it scales every input in the same way up to phase. MIMO complication in MIMO systems, d omega and y omega are vectors, so their size must be measured using a norm. You should have seen this in linear algebra course, that when we have vectors, we size them using the norms, and we have different kind of norms. We have two norms as the most common norm, because the two norm represents the total amplitude or energy when multiple actuators or sensors contribute simultaneously. So we have so from our last example, we have this, or latest example, we had this example where we talked about a two input, two output system, and then we talked about how each input affects certain output. So we had input channel J, which was effective, or input channel 1, which was affected by both the output channel 1, which was both affected by input channel 1 and input channel 2. So we need to find ways to assess the output. So we need to essentially define methods to evaluate each output. So again, let's assume that you have two actuators firing at once, and what does input size even mean? And this motivates norms as physically meaningful aggregate measures. So norms are physically meaningful aggregate measures. The two norm is like root mean square. Root mean square magnitude across channels. So if you look at the sigma under the root square, we have dj omega, all absolute values of dj omega, and then we square them, we sum them, and then we take the root of that root square of that summation, and the squared sum resembles energy-like quantities, right? Strictly speaking, energy depends on units and weighting, but this is the right intuition for you, meaning that it is true that if we talk about energy, we have to be sure that the unit is correct. But then this, when I say this resembles somehow, or represents energy somehow, this square sum resembles energy-like quantities. I'm talking about energy-like quantities, and I want to give you a sense of what this square root is and why two norm represents essentially the most the most common used norm among all norms. In industry, engineers sometimes use weighted norms when different sensors have different units. Um, this is just true somehow. You can keep this in the back of your mind somehow. At some point, we're going to go back to that. We're going to talk about that further. But they talk about weighted norms because sensors have different units, and we need to find ways to adjust units so that when we add various quantities together, it makes sense. That is why they do it. All right. For a given input direction, the gain is y omega 2 norm. So we have two vertical lines on the left and right at quantity. This is a 2 norm of d omega, and then this equals to gj omega d omega, again substituting gj omega d omega for y omega, and then continue simplifying this this fraction. Let me remind you what direction essentially means practically. Direction is the relative pattern across actuators, which one pushes, and how hard, and with what phase. So direction talks about which actuator is activated, how hard, and with what phase. Think of a 2D arrow in input space. You might have same length arrows in that space, but they might have different directions. You might have same arrow in the same different pointing in different directions, and they have different magnitude as well as different directions or different phase. This is the multivariable analog of y over d. This y omega 2 norm over d omega 2 norm is the multivariable analog of y over d, but it now depends on the direction of input vectors. So I've not gone through the same simplification. I've not cancelled d omega from top and bottom. You can notice that. But it's the multivariable analog of y over d, except y omega and d omega in this case are vectors, and therefore you have to use a norm to size them and make so to measure their size. In MIMO, in MIMO, gain depends on direction. This is the conceptual difference between SISO and MIMO. It depends on direction. In SISO, it does not depend on direction because the direction as we know it for MIMO makes there's no direction in the same way as it exists for MIMO, multi-input, multi-output systems. So let's consider this mechanical intuition. In two actuators may apply the same total effort, but depending on how their signals combine, they may strongly excite a mode or partially cancel it. Consider, for example, two shakers on a plate. If they are in phase, they excite bending mode, and they are out of phase, they excite torsional mode. In both cases, you have same total effort because you're applying the same excitation. But then you have different modal participation because the phase varies between case 1 and case 2. So you can spend same energy, and still get almost nothing if you excite the wrong direction. The maximum gain, let's define the maximum gain over all non-zero inputs. So again, we have G, D2 norm over D2 norm becoming max GD2 norm equal sigma bar G. This is the maximum singular value. So to explain this, this further note on the gain, we want to compare directions fairly, not by using a bigger input, right? We don't want to compare the biggest input with the lowest output, right? Among all directions with equal effort, one direction is worst case. So among all directions with equal effort, one direction is worst case. Among all unit lengths input direction, among all unit lengths input direction, there exists a worst direction that produces the largest output. This also relates to robustness. Worst case scenario, worst case amplification matters when disturbances can come from anywhere. Again, worst case amplification matters. Worst case amplification. It does make sense because you have to care about worst case amplification. But then disturbances could also come from any direction, any input. And then as opposed to maximum gain, we can also define the minimum gain. The minimum gain over all non-zero inputs is GD, again, 2 norm. So we are still working with the GD2 norm over D2 norm, and D was the input vector and the G was the matrix, and then GD was coming from output 2 norm. Output was a vector, and then we replaced that in this ratio with GD. So the minimum GD2 norm over D2 norm, obviously for D non-zero, equals minimum GD2 norm, or when the D2 norm equals 1, and we call this sigma underscore G. This is the minimum singular value. So maximum singular value and the minimum singular value. Some directions. So let me add some notes to this relationship. There are directions that barely get through the systems. This is crucial for controllability at the frequency because we need to know which directions barely get through the systems. And if we excite the system along those directions that barely get through the systems, we need to know how that affects the controllability at a frequency. And then it also matters for estimation observability and sensing. And then it also matters for the system to identify if the system is ill-conditioned or not. We're going to go back to that again. So some directions are weakly amplified or nearly cancelled. These directions are critical for estimation and robustness. Let's see how this relates to sensors. If your sensor array is aligned with a weak output directions, you will struggle to measure what matters. Again, if your sensor array is aligned with a weak output direction, so you don't know where to put your sensors, and you have accidentally aligned your sensor with a weak output directions, then you will struggle, as it makes sense, you will struggle to measure what matters. This is not what matters. You care about something else. Maybe you care about, and you should care about, worst case scenario, the maximum amplification. Let's go through an exercise and talk about how direction affects the output. All 5 inputs below satisfy D2 norm equal to 1, but because we're talking about unit energy, and that's why, again, in this definition we also talked about unit energy. Unit energy, obviously we're talking about, energy like input, because we're talking about 2 norm again. But let's go back and let's restart this exercise. We're going to talk about how direction affects the output. Again, once you see this the exercise, please spend some time solve that before resuming to watch the video. So for now, after I describe the exercise, please pause the video and then work out the exercise by yourself, and then continue watching the video. All 5 inputs below satisfy 2 norm equal to 1, but point in different direction. Is 1 0 0 1. Think about the 2 axes into the plane, and then they all point in different directions. But in all cases, 2 norm is equal to 1. So the energy is equal to 1. So from this point on, when I say energy, I recognize the fact that I'm talking about an energy-like quantity, and I know it. So for G equal 5 4 3 2, while J is equal to DJ, apologize, and compare. I think I made I compared the gains. Now I want you to compare the gains for 2 norms of YJ2. So don't pick on this using J for both input and output, because in this case I mean different. I just want to make sure that we are comparing output corresponding to one input to output corresponding to the next input. So you need to compute Yj using matrix multiplication you have here, and then once you quickly compute that, you can compute the 2 norm for every output, and then you can rank the results. Okay. And also let me add one more point here. When you look at D3 and D4, you can kind of see where it goes. For example, in other words, you can think about how 707.707 and D4, which points at a direction which makes a certain angle with this first direction, how that affects the output. So in many physical systems, this corresponds to symmetric vs anti-symmetric modes. If you recall from your vibration mode, you did talk about symmetric and anti-symmetric modes. And ask yourself, essentially, before going through the computations, that which one, or which direction do you expect to excite the system more? For example, D3 or D4. Okay, so in how symmetric excitation works out versus anti-symmetric excitation. Before you do a computation, think about physical interpretation of that. And this is the whole idea, or the whole reason behind this exercise is to see why singular values matter, to summarize the best and worst case scenarios. We have already seen that. Let's go here, or let's just start from here. Again, now we're going to talk about eigenvalues. As I saw reminder, for a scalar system, the frequency domain gain is simply the magnitude of g j omega. There is only one input direction and one output direction. So gain has unambiguous meaning, right? This is from SISO. We have already reminded, I have already given you this reminder many times. So gain in SISO is easy. It's one number, one meaning. There is no ambiguity because there's only one input and one output. And you might be tempted to consider the following idea. Use eigenvalues of the frequency response. So eigenvalues of the frequency response. If eigenvalues of the frequency, there is, but this is problematic, or you already know that, because there's no choice of direction. If you consider this eigenvalues of this matrix, essentially what you're saying is we don't care about direction. We don't care about geometry. This is wrong. This is problematic. Okay. But this is a natural mistake, meaning that you might, even engineers, right at the beginning might try eigenvalues first because they worked well for poles and stability. So you might be tempted to use eigenvalues, but eigenvalues are defined only for square matrices. Even when they exist, they describe behavior along very special direction, the eigendirection. So eigenvectors or eigendirections are not generic input directions. They are highly structured and rare. This direction is subtle but crucial. So we're only talking about eigendirection, obviously. Let's think about a counter example just to demonstrate how this assumption about or using the eigendirections and eigenvalues is problematic. Consider the following matrix G, 0, 100, 0, 0, both eigenvalues are 0, the gain is 0. For the input 0, 1, y equals GD 100 and 0. I'm just double checking the computation. 0, 1 is 0, 0. This is correct. 1, 0, 0, it results in 0. But then, as you see, the gain, at least from here, you see that the gain is very large because it's 100 and 0. This is because input 2, right? If you think about it, and not input 1, because you have output channel 1, but then you have input channel 2. This is because input channel 2 strongly affects output 1. Everything else is 0. So eigenvalues essentially are telling us nothing happens, but then this conclusion that the eigenvalues tell us everything is wrong. This conclusion is disastrously incorrect. It's far from correct and far from the actual response of the system. All right. Now let's see what eigenvalues actually measure. Now that we have realized that eigenvalues are not correct measure of how strong the response is and in what channel, think about it further. Let Ti be an eigenvectors of G with eigenvalue lambda I. If the input is chosen as D, then Y is equal to G Ti lambda I Ti. This is because this is our eigenvalue, so GTI is equal to lambda I Ti. And what we expect is 2 norm being 2 norm out, not be expected, but defined as 2 norm output or 2 norm input being lambda I. So eigenvalues describe what happens only if you excite the system exactly along eigenvectors. So you have to exactly excite the system along eigenvectors. The real disturbances do not politely align with eigenvectors. Not necessarily. So they might align somewhere between eigenvectors, for example. What does it mean? It means that eigenvalues measure gain only when the input happens to align with a special direction or eigen direction or eigenvalue. And what does it mean in practical sense? This can be relevant for internal dynamics, but it is not suitable for performance or robustness analysis, because robustness relates to the actual response for the actual input, and performance the same way, and stability same way. Eigenvalues are excellent for internal stability, for modal structures. Why do we say internal stability? Because then internal stability may not be explained as something relevant to output in external excitation. So that's why we say internal stability. But they are poor for worst case amplification, the actual response of the system, or robustness to unknown disturbances. So before moving forwards in matrix, for matrix norm, to generalize the notion of gain, we use a matrix norm, because we're going to use that. Two essential properties of matrix norms are the norm of G1 and G2 is less than or equal to norm of G1 plus norm of G2, and norm of G1 multiply G2 is less than or equal to norm G1 norm G2. These ensure that size behaves consistently under addition and cascade of systems. The spectral radius is another definition. The spectral radius of J is equal to max lambda I G is not a matrix norm, but rather a separate definition. And common, you might think of rho G as a measure of system gain. This interpretation is incorrect. And then reason for that is that the spectral radius does not satisfy the norm axioms, in particular multiplicativity. Sorry, it's hard for me to pronounce that. In contrast, the spectral norm is 2 norm G is equal to sigma bar G. And then let me see. Vector norm. We talked about. Oh, let's consider one more simplified interpretation. The spectral norm is the largest possible amplification of signal energy by the matrix. Largest possible amplification of signal energy by the matrix. It does not satisfy the required norm properties, in particular submultiplicativity. Let's think about a simple example, and we're going to use these concepts and these relations later. Consider all unit vectors, and when we say unit vectors, it simply means 2 norm is equal to 1. The spectral norm is the maximum length of Gx over all such directions, all directions with 2 norm equal to 1, just like the latest example we saw together. So in other words, a spectral norm is the worst case gain over all directions, and the spectral rate the largest eigenvalue magnitude. So the spectral, let me add some more explanations. The spectral radius only looks at what happens along special directions. As when you look at the definition, you can already see that. It looks at eigendirections. The spectral norm looks at all possible directions, but then the spectral radius looks at special directions. So a spectral radius, which looks at a special or eigendirections, and a spectral norm looks at all possible directions. A matrix, a G matrix, can strongly, I apologize. Just give me a second. Actually, let's stop let me finish that. Let me see how many. Oh, okay. And then yeah, let's finish up that course here, and then I'll continue in the next section, next slide, next video. Thanks.